Hello everyone, welcome back to another presentation of Ingis Education. In today's presentation, I'm going to talk in detail about my solar tracker project. Now, many of you who has been following me over the years, you know that my first project in this channel was this solar tracker. But since then, I moved on working with Raspberry Pi and in my full-time education. So I've got little time to review my project and go in detail. Now in today's video I would like to give you more information about my project. Also I would like to give you the link of the dissertation paper, so where you can go and see in detail how did I do it. A similar kind of project I have seen done by other YouTuber as well, but my one obviously I try to follow everyone and I try to get feedback from everyone. That's the way you learn in modern times. Now let's talk about the objectives of this project. Study the power gain by the existing solar tracker technologies and compare to the fixed angle PV unit. Explore the power gain of single axis solar tracker compared to the dual axis solar tracker, analyzing the general cost effectiveness versus the power gain, identifying the issues affecting the least frequent use of the system, recommendation of the system improvement to make it more usable, modeling an efficient physical prototype of a small scale solar tracker with Tetrix robotic kit and solar cell for detailed study, outlining the system potential implementation for large scale use. Now I will share my dissertation with you. So this is the literature review part of the dissertation. I try to get some historical background of the solar tracker. From there you can see I mentioned quite a bit of history. The most notable one is that McPhee R 1975 first developed automatic solar tracker incorporating an algorithm computing total receiving power and distribution of the flux density in the central solar power system, and the system did operate higher degree of accuracies than SEMA RP and Emura MS 1981, almost 40 years ago, applied more modern method of incorporating microcontroller to control the photovoltaic concentrator automatically to the optimum angle of the sun. Now the background theory of the solar tracker is that before investigating the solar tracker mechanism, first it is required to understand the orbital relationship between the earth and the sun. The earth spins around the sun, causes the day and nights variable. This figure shows that earth with different rotational axes and imaginary angular coordinates used by astronomers and researchers to explain the Earth's nature of rotation. There are two different rotations the Earth is involved around the Sun. One is the daily rotation concentric to an imaginary line. This is the imaginary line connecting North and South Pole, caused day and nights to happen. This is the rotational axis, and the other axis is concentric to the sun eastward throughout the stars, called ecliptic rotation. So this is the North Pole and South Pole connecting line, and this is the orbital rotation line. You will find everything in my dissertation paper with the link provided. Now there are different kind of solar tracker has been developed. This is a manual tracker which you rotate manually. There are certain advantages and disadvantages. Let's not talk more detail about this. This is a two angle solar tracker, so this is like x axis and this is around the z axis. There are passive solar trackers without any electronics. These are basically liquid inside. It works with the expansion of the liquid. So with the hot sun, the liquid get expanded. That shift the balance of the weight ratio and the solar tracker moves with the sun. This system is not very efficient. Now these are the hardwares I have used for this project. This is the working mechanism of the project. So the input, I put the input with the switch button, and the microcontroller I've used that National Instrument Myrio. The servo motor and the stepper motor I have used. PV cell, I've used one small PV cell. It gets the feedback from the sensor LDR, light dependent resistor. So these are the list of the hardwares I have used. This is the motor controller board I've used for my Raspberry Pi smart robot as well. Now I have modeled all the things in Autodesk Inventor. This is really good for visualization and for 3D printing as well. This one I have printed 3D. So this is the complete working machine here, as you can see, with the 10-volt power source and National Instrument Myrio motor control board. This is the electronic schematic of the system, and this is the graphic user interface from the lab view user window, where you can see my 4 LDR system, sensor, and this is like bit like oscilloscope. You can see the feedback from the 4 sensors overlapping each other. You can calibrate them with this user window. I did quite a bit of prototype testing. Now the performance analyzing, what I found is that this yellow marker showing in the graph that price projection full size PV cells versus the solar tracker. Now I did quite a bit of mechanical engineering stress test, because this is the solar tracker housing enclosure. In between these two hand, the solar PV panel will be seated, and here the LDR will be seated. I did the stress test so that it can withhold all the weight it will get. These are more like a project management kind of thing. With the Autodesk Inventor, I created a bill of materials, so you can see all the components I have used. Unfortunately, I don't have the AutoCAD file with me at the moment, otherwise I'd be able to share with you guys. These are the results from the stress analyzing. That's all. I'd like to end this video right now. If you like this video, please press the like button. Also, don't forget to like, comment and share. I will see you at next time. Thank you very much.